For a start, so theorem 2.20, so chapter 2 is the 20th thing, given a numerical ID, an integer ID in the chapter. And here's the theorem statement. So a language is context-free if and only if, so IFF, some PDA, push-down automaton, some PDA recognizes it. Okay. Now, as usual, I've circled there are two mathematical statements here in this larger mathematical statement. So a language is context-free. I call it statement P, if and only if, and then some other statement, call it Q, which is some PDA recognizes it. So P, if and only if Q. Right? We've talked about this kind of thing before. And remember, if and only if type proofs are two parts. You have to prove it one way and you have to prove it the other way. It's a two-part proof. That's typical of if and only if type proofs. Okay? Now, Sipser claims, or he states, that both directions, proving it both ways, are interesting. Right? Getting one from the other is as interesting as the other from the one. Both it's not as though one direction is sort of trivial and the other one's interesting. They're both interesting. So and long. The proofs of these are several pages. Now, these proofs are getting quite substantial. Right? I'd say either a bright senior can follow it fairly readily, or into M1 level, I'd say. Okay. Now, so Sipser is now going to, and let me get rid of this. Sipser is going to prove the relatively easier direction first, which happens to contradict the pretty strong convention amongst pure mathematicians to prove the if case first. Mathematicians are so accustomed to that if someone breaks it, it's annoying, because when pure mathematicians, when they see an if and only if proof, strong convention is that it's the if. So if you have a mathematical statement, theorem statement of the form P, if and only if Q, then the mathematicians will expect that the first part, it's a two-directional proof, that the first part will be the if part. In other words, P if Q, which translates to Q arrow P. Okay. But Sipser's going to do the other one first, the only if, effectively. So he's going to do the P arrow Q one first, okay? Which is so as he did before, he's going to take these two parts of the if and only if proof and make a lemma of each of them. So he'll create two lemmas, and remember, lemma is just sort of a preliminary mini proof. That doesn't necessarily mean it's small. It's just a sort of smaller than the bigger proof that incorporates the results of these preparatory mini proofs. Okay, so he's going to do P arrow Q first. That's the only if, and he's going to start with that one, despite, well, maybe he's not even aware, I'm not sure, of the pure math convention. It's quite strong. So he's going to prove in this lemma, and here's the lemma statement, sort of like a theorem statement. So if a language is context-free, then some PDA recognizes it. So in other words, if P then Q. So if a language is context-free, some PDA recognizes it. So if P then Q. Right? So that's P, some PDA, that's Q. Right? So if P then Q, he's going to do that one first. So look at what the statement's saying. In other words, you've got some language, and you're assuming, if you're assuming that that language is context free, then there'll be some PDA that can recognize that language. Okay, that's the statement. So you have to design some PDA that can recognize the language, and the strategy is to design a PDA that behaves like the grammar. So see if a language, a context-free language, a CFL, what is that? Well, by definition, it's a language that is generated by a grammar, a context-free grammar. Okay? So if a language is context-free, that means there's some CFG, some context-free grammar that generates it. Okay? So if we can create a PDA that behaves like that grammar, that context-free grammar that generates this language, well then we can prove this, right? Because if the PDA behaves just like, is equivalent to this grammar, right? Then the two of them, the grammar and this PDA, will detect the same language. They will recognize the same language. They will accept the same strings in the language. Okay, so that's the strategy. So the broad idea is design a PDA that behaves like the CFG, that behaves like the grammar. And what does a grammar do? Now that may sound a bit strange, because what's the connection between a PDA and a grammar? Well, what's a grammar do? It's deriving a string, right? I mean, what is a language? Just a set of strings. So a grammar, from the grammar, you can generate all the strings in that language. Okay? So if you can design a PDA that does the same thing, behaves in the same way, step by step, as a grammar behaves. Now what's a grammar doing? Well, you'll start, when you generate a string using a grammar, how do you do it? You do it in steps. You start with the start symbol, capital S, okay? And then you use your substitution rules in your big R to step by step substitute variables in your intermediate string. So you'll start with your S, capital S, your start variable, and then you'll start using substitution rules to modify the intermediate string that you generate each time. Like you look at the current string that you have, that you've derived from earlier steps, and you look for a variable in that string, and then you look for a rule in your rule set that has that variable on the left hand side, and you choose one, and then whatever's on the right hand side of that rule, you then throw out that variable in the intermediate string, and you replace it by what's on the right hand side of the rule that you chose. Okay, so and that will yield, that's the technical term, that will yield a new intermediate string, and then you look for another variable in the new intermediate string and substitute again using a rule, and so on. So each time, each step, you're yielding a new intermediate string. Well, if you can have the PDA do much the same thing, for example, it could use its stack to store the intermediate string, that progresses step by step. Now there are complications. We'll have to well, I won't go into it, but there are complications. But you get the general idea. I mean, you can get a PDA to behave like a deriving grammar, right? You can, for example, you could put the start symbol on the stack. That is the start symbol of the grammar, right? But you put that on the stack, and then you use rules to change the contents of the stack, which are equivalent to intermediate strings. So the main idea, I keep saying, the main idea is to get your PDA to behave like a grammar, a context-free grammar. And if you can get that, if you can get the PDA and the context-free grammar to describe the same language, well, then those two are equivalent, right? And since the grammar describes the language, by definition, a context-free language, a CFL, is described by a CFG, right? The grammar. But if the grammar and the PDA are equivalent, well, then therefore, then the language and the PDA are equivalent, right? That's just by that's a transitive relation. Like if A and B are equivalent and B and C are equivalent, then A and C are equivalent. Okay, so the language is generated by the grammar, CFG, but and let's say we can prove, so the CFG and the PDA are equivalent, so that means that the PDA can generate the language, okay, or recognises it. The PDA can recognise the language, so if that, then this. So that's how you prove it. That's the broad strategy. That's sort of like the proof idea. Okay, so you just get the PDA to behave the way a grammar generates a string. It derives the string. So it starts with the start symbol. It goes through a whole series of steps of creating an intermediate string by substituting variables for the right-hand side of the rules that match the variable, until eventually you get a string that's all terminals. Okay, and that terminal, because it's been derived from the rules of the grammar, that terminal will be that terminal string will be a member of your language. Okay. Now, if the PDA can also generate that string, then it's equivalent to the grammar. Okay. So now, next session, we'll start getting into the details a bit of how to design a PDA that behaves as if it were a grammar, context-free grammar, CFG. Ciao.